So suppose I take constant flux conditions, so the local flux Qs is h into Ts minus Tm, and that's constant, right. So which means that dTs by dx should be equal to dTm by dx, right, because it's constant. So all I have done is I have taken the first derivative with respect to x position. So the gradients of these two have to be equal. So now if I plug in that condition there, okay, so we will see that 0 equal to minus dt by dx plus Ts minus T divided by Ts minus Tm into dTm by dx, okay, plus, so that will be, so Tm minus T divided by T minus Tm divided by Ts minus Tm into dTs by dx, okay. So now I can replace dTs by dx with the gradient of the average temperature, so that will be dTm by dx, okay. So now if I join these two together, so you will find that dt by dx, that's equal to dx, and that's also equal to dTs by dx. So all I have done is I have just clubbed these two, so the local temperature term will cancel out. So what you will have is Ts minus Tm, and so you divide by Ts minus Tm, that goes away. So what you have is that the local temperature gradient in the x position should be equal to the local temperature gradient of the mixing cup average, and that should also be equal to the temperature gradient of the surface. So that's an important insight. So we have got two important things. One is that the heat transport coefficient remains constant in the fully developed regime, and not just that, the gradients are actually equal. Again, this is in the fully developed regime. So the gradients are equal. So this is an important piece of insight from experimental point of view. Okay. So if I know how to measure the local temperature of the surface, I'm done. I can find the temperature gradient of the fluid inside the tube. So typically the entry region is very small. So by and large it's going to be a fully developed regime in the tube, and so I should be able to estimate the temperature gradient of the fluid inside the tube just by looking at the surface temperature. So that's an excellent method to measure experimentally. So such kind of an insight is very difficult to get from experiments. By looking at simple analysis of the nature of the solution, we are able to estimate an important property of the system, that the temperature, local temperature gradient in the x direction is same as the temperature gradient of the surface. Okay. Alright, so one could do the same exercise for constant temperature also. So one could do the same exercise for constant temperature. So you will see that dt by dx, that will be Ts minus Tm for Ts minus T divided by Ts minus Tm and dTm by dx. So this is for the constant temperature case where dTs by dx is 0. So if it's constant temperature, then the temperature gradient in the wall is 0, and so we will see that dt by dx is Ts minus T by Ts minus Tm into dTm by dx. Now is this a function of radial position? Of course, yes. Is this a function of axial position? Yes or no? Is it or no? It's not. This is dimensionless temperature. This is dimensionless temperature. dTm by, yeah, okay. So, okay, good. So this actually can be a function of axial position, because although you have a dimensionless temperature here, the gradient dTm by dx, we don't know anything about dTm by dx. So dTm by dx can in principle be function of x. So now the real exercise, once we know this, the real exercise is to find out what is the cup mixing temperature. So can we find the cup mixing temperature? So if we find the cup mixing temperature profile with respect to x direction, then we are done. We get a lot more piece of information without solving all the gory equations. Okay. So what we are going to do next exercise is to find out what is the method to estimate the cup mixing temperature. So what we are going to write is we are going to write a balance, energy balance for estimating cup mixing temperature Tm. Okay. So this is very similar to the lumping I talked about during conduction. So if you have a full temperature profile, you can actually integrate in the radial direction and you would actually get a same energy balance, and it's a good exercise to try it out. Okay. So suppose I take a tube, okay, this is dx, and if the mixing cup temperature at that location is Tm, and this is Tm x plus dx, this is x, okay. And if the mass flow rate is m dot, and if the amount of heat that is lost is dq convection, okay, so that's the total amount of heat that's lost from the surface. So what's the heat balance? Whatever heat that is coming into this shell at this location should be equal to what leaves plus whatever is leaving from the other end of the shell, right? So that should be dq convection, okay, plus what is the amount of energy that is actually leaving this place, this location? Yeah, m dot, okay, so m dot Cp into Tm, right, at x plus dx minus m dot Cp Tm at x equal to 0, right. So that's the total amount of heat that is actually entering this and leaving this place, okay. So from here, is the sign right? That's okay. What about the yeah, there will be conduction. This is the overall balance, right? So conduction is accounted here. This is no, be very careful. This is the mixing cup temperature, right? Now when you want to write conduction, you have to write the local temperature. So here we have lumped everything. It does, it takes place in the z direction, right? But whatever heat comes in and leaves, everything is accounted in the total amount of accumulation. Right? This is the amount of heat that is carried, net amount of heat carried by the fluid. Now this can be split into two parts. What's the diffusion, what's the conduction term and what's the convection term? It could be split into two parts, but this is just a generic balance, okay. So from here, so what is dq convection? So if the flux of heat transport is q double dash, okay, we don't know whether it is constant flux or not. Let's say in general the flux is qs, so it could be a position of x, okay, multiplied by the perimeter, right, into dx, right. So that's the convection, right. So therefore if you plug this in, you will see that qs double prime that right? Okay. So I can rewrite this as m dot Cp into dTm by dx, that should be equal to minus Qs into P. Okay. So how do I define Qs? What is Qs? If it's a constant flux, then this is constant for first case. If it's a constant flux, then this is constant. If it's constant temperature, Qs is given by some heat transport coefficient multiplied by Ts minus Tm, right? So I can plug that in. So that will be m dot Cp into dTm by dx, that's equal to h into Ts minus Tm into P. Yeah, you need a temperature gradient, right, for flux. What's the Newton's law of cooling? The flux will be equal to heat transport coefficient multiplied by the temperature of the surface minus whatever is the reference temperature. So the reference temperature for our problem is the cup mixing temperature, right? So that's the reference temperature. Yeah, it's the cross sectional average. Tm is the cross sectional average. Correct. So that's a weighted cross sectional average. It's still a cross sectional average. You have to take the velocity into account because the u can be different at different locations, right? So you have to take, if you want, yeah, at a given cross section, you have a velocity profile. It's not a flat velocity profile. You have a parabolic velocity profile. So therefore, you have to take into account the effect of the velocity on the amount of energy that is carried. And that's why Tm will account for the local velocity and also the local temperature in the fluid at any cross section. So it's a cross sectional average weighted with the velocity term, weighted with the profile of the velocity. So suppose I find for the constant flux case, so dTm by dx will be equal to minus Qs prime into P by m dot Cp. Okay. So I know this, and if it's a constant flux, the flux is a measurable quantity. So I know what Qs is, I know what P is, I know what m dot and Cp is, so I should be able to find the temperature profile, right? So I can find out what C. Obviously it's linear, you can see that. Okay. Now if it's a constant temperature, the constant temperature case, I could still solve this equation. So it will be m dot Cp into dTm by dx equal to heat transport coefficient into Ts minus Tm. Okay. So now here the mixing cup temperature is now going to be a function of the heat transport coefficient. What will be the mixing cup temperature profile? It will be exponential function, right? Minus sign into P, that should be a P, right? So that will be a function of the heat transport coefficient. And so you can clearly see that when you have constant flux, the temperature profile is going to vary linearly in the fully developed regime, while in the case of constant temperature, it's going to be an exponential profile. So one can actually draw the temperature profile, okay, for a constant flux case. If I draw the temperature profile for constant flux, okay, so you will have, so remember we said that for constant flux case, dTm by dx is also equal to dTs by dx, that's also equal to dt by dx in the fully developed regime, right. So remember the derivatives we took a short while ago. So there we clearly showed that for a constant flux case, the gradient of the mixing cup temperature is equal to the gradient of the surface temperature and the local temperature in the fully developed regime. So, if this is the temperature profile of the mixing cup temperature, and this will be the temperature profile of the, this will be the surface temperature, okay. So, that will be the surface temperature. So, the surface temperature gradient, this is the fully developed regime. So, the surface temperature gradient and the mixing cup temperature gradient are same in the fully developed regime, while they are not same in the entry region, okay. So, in fact, this is the reason why the heat transport coefficient is actually significantly higher in the entry region. So, remember we drew this plot of heat transport coefficient versus x, where you have a constant heat transport coefficient in the fully developed regime, and that is because the gradients are equal and also the mixing cup temperature is linear. So, therefore, the gradient is constant when you have a constant flux condition, and therefore, the heat transport coefficient has to remain constant for a given set of properties like conductivity of the fluid, while in the entry region the gradient is very small and therefore, the heat transport coefficient has to be very large. No, you can always have the reverse. If you have, so we started the discussion by assuming that there is heat transport from the outside to the inside of the fluid. You can always do the reverse, it does not matter. The profiles will be different. Yeah, sure, because this balance we wrote, this is for the whole tube going from 0 to L. This is independent of whether you have a fully developed regime or an entry region. This balance is valid everywhere in the tube. So, it is linear everywhere, but the surface temperature is not linear everywhere. Why does the? Right. Because the fluid is now, so the mixing cup temperature is now catching up with the temperature of the wall, right. So, wall temperature is higher, it is going to catch up with the, right. No, but this is constant flux. Keep in mind that this is constant flux, not constant temperature, right. So, you are only removing constant amount of heat. So, the temperature of the wall is the one which is going to vary with the actual position, right. You are supplying or leaving, whatever, it does not matter. Whether Ts is higher than Tm or Tm is higher than Ts, you will have exactly a similar behavior, except that the profiles are going to be slightly, so Tm is going to be higher than Ts if you are actually removing heat from the fluid. If you are actually supplying heat, then this profile is going to be above the Tm, that is all. That is the only difference. Any questions so far? So, remember that we still have not solved the full profile, okay. So, without solving the full profile of the temperature, we are able to get a lot of insights into what is the nature of the heat transport coefficient, what is the nature of some of the observable quantities like the surface temperature, and in fact, we are able to predict some of the properties of the actual temperature profile without even solving the equations. We will come to solving the equations in the next lecture.